Well, hello there. Today is our last lecture, and we'll spend it rather splendid on the fantastic topic decision trees and So we will consider this another fabulous computational model of decision trees, and then we will use it to talk about this the threesome problem, one of the model problem to sharpen your algorithmic skills. Okay, so what is a decision tree? A decision tree is a way to understand the input by asking us some simple questions. So it is obviously a tree. Sometimes it's binary, sometimes it could be non-binary, that's also all right. It might not be balanced at all. So, and the idea is that we have a question about input at every node of this tree. Those are usually some simple questions. If you ever played this game about 20 questions, where you think of a character or a famous person, basically any area you specified ahead, and then the other player tries to find out who you're thinking about by simply asking you yes or no questions, and it turns out that 20 is more than enough to get that character or that actor or whoever that is right, almost all the time. So that this is basically our way to build a decision tree. So you can actually try to construct that thing where you're like, hey, is this person and in the movies? If yes, you go here. If no, you ask something else. You is this person younger than 30, and so on. So you have those questions, and just by following the path in this tree, you can have this. You can get to the leaf, and in leaf you have an answer. So this, for example, your first question is it an actor from the Marvel, right? And your second question is, and this is yes, so Marvel. Okay, let's make it right, and then you have this question: is it a human being, right? Human. Okay, and then you ask something silly. For example, does he or she like 80s music, right? And let's say this is yes, and this is yes, and then you like Star-Lord. Yes, Star-Lord. Sorry if that was a little bit too cringy for you, but yeah, this is how it works. You narrow down your ability, your like, especially in the area of decision trees are heavily used in machine learning, in the processing of data, where you say, hey, I have my huge data, how can I understand it? And the way to understand it is to clusterize it. And but that's not enough. You can say, hey, I have this tree that, like, splitting my data into clusters that are like separate from other clusters by those questions. And the further down the line is my ancestor from another cluster, the less common things we will find, right? Okay. So now what we're gonna do, we're gonna try to construct some decision trees for some actual problems. All right. So the problem we are looking for is a three-sum problem. There are two different definitions. We will go with one of them. This is so three-sum problem. You have your input. Numbers A1 through AN, B1 through BN, and C1 through CN, all just some integers. And let's assume that we can interact with integers in constant time, so we are not bothered by their size. Output, are there so I'm looking for a triple of indexes I, j, and k, such that ai plus bj plus ck is equal to 0. All right, so in terms of algorithms, there is clearly an algorithm that runs in n-cube time, right? So the brute force, as we discussed before, can just run through all the triples of numbers, check if they're equal to 0 as a sum, and then move on or output that triple. So what I'd be interested in is to solve this problem via decision tree. So I want to prove that decision tree complexity of a three-sum is at most, we'll start with order, it's order n square. With decision trees, I will consider that I have, so when we create a decision tree, there is always the question of what can we put in the nodes? What kind of questions can we put in nodes of the decision tree? So my questions would be less or equal. So what I want to know is, I want to compare the sum of some elements, some constant number of elements with some, well, not some, just some linear combination of some elements with some linear combination of other elements. So the typical question would be, is a 1 greater or equal to b1 plus cn? This would be actually our very first question. So that would be the typical thing to do. So another way to put it is, I can state this in another way. I can state this as a1 minus b1 minus cn greater or equal to 0. This way we can define my questions as, is this linear combination of numbers from the input greater or equal to 0. All right. So I want a complexity of n squared. How do I do that? Well, first of all, we need to sort the inputs. We need to sort the inputs, and I'm not quite sure that we haven't covered sorting in this class, and I'm not quite sure if that is something you are comfortable with, but you would have to believe me that you can do sorting by a decision tree in order of n log n. Right? So this is a paramount thing, that decision trees can actually sort numbers. So all you need to do would be to compare one element with another element. So I want to span the beginning of the decision tree. So my top decision tree would be sorting. So I want to sort all the A's, I want to sort all the B's, and I want to sort all the C's, so that the depth of the beginning of the decision tree would be order of n log n. All right. So now every path here lead me to a node in the decision tree where I know the increasing order of A's, increasing order of B's, and increasing order of C's. So I'll just call those. So I have A1 prime less or equal to A2 prime, and so on, less or equal to AN prime. So with B's, okay, so at this node I have this reordering of the original arrays that now are sorted there, sorted in increasing order. Okay, what do I do now? Let us consider my three arrays. I have A's, A primes, B primes, and C primes. So, and what I will do, I will first check if this little guy, A1 prime, is a candidate for the answer, right? So I will check if I could be equal to 1. And I will do that in linear time, and then I will repeat it for all the indices I from 1 to n. So what I need to do is to check if there exist J and K such that A1 prime is equal to minus B1 Bj prime plus Ck prime. All right. How are we going to do that? And I also still need to do that as a decision tree. So I have now my decision tree. So the first part was just sorting. So that's not interesting. Now the question is what's going on in here, right? So what it would be my first question over here would be, is it true that A1 is greater or equal to the minus Bj prime minus C, will be B1 prime minus C n prime. And immediately, if the answer is no, it's one possibility, and if the answer is yes, I want to just immediately ask the opposite question: is A1 prime less or equal to the minus B1 minus Cn prime? And if the answer is yes again, then we output that yes, the answer. So we found that those things are both true if A1 prime plus B1 prime plus Cn prime are equal to 0, which means that we found our answer. So those two are our basically options if we failed to find the index. So we compare this plus this plus this. And suppose we are here, which means that we now know that A1 prime is less. So let's put it this one: A1 prime plus B1 prime plus Cn prime are less than 0. All right. Okay. My question is, can it be that there exists a K such that A1 prime plus B1 prime plus Ck prime is equal to 0? And the answer is definitely not. How so? So we know that Cn prime is the largest number among all the C's. So that means that this thing is less than this thing. So this whole thing is definitely less than 0. that means that Cn cannot, or that B1 is not part of a triple, that J couldn't be equal to 1. So that means that we kind of forget about this guy and just move on over here. So from now on, so here our question would be A1 prime greater or equal to B2 prime minus Cn prime. Right? So, and then you have the opposite scenario. So if you end up here, what will happen, right? So we're still in this scenario. But now we know that it's greater than 0. So then the question, can we still have Cn prime on our team? And the answer is again no. A1 prime plus bk prime plus Cn prime. So this is right greater or equal, which means that this is greater than 0. This is a horribly written A, so this is A. Okay, so that means that we are losing Cn as our candidate. That means that, I already used K here, L. That means that N couldn't be part of our triple. That means that we kind of can just discard Cn, so this is not valid anymore, and we just move on to this one. So this question would be A1 prime greater or equal to minus B1 minus C and minus 1 prime. So yeah, that's how you do it. So you need to, so every time we ask a question here, we either push this element further or this element down, right? So we have only at most 2n steps we could take. So we can push this one up at most n times. We can push this one down at most n times. And then we either find the right element or we didn't, in which case we are done. And then, so the whole thing will take a linear number of questions. And then we need to repeat it for every index I. So we need to do it for A2, A3, and that up to AN. So this whole thing would be order of n squared. So that is a decision tree that is solving threesome and has depth of n squared if we could use a linear combination comparison with 0 as our questions. And in this particular case, it turns out that we used only combination of 3 elements. So we had sums of 3 elements that we're comparing with 0, and it turns out that if that is the class of questions you're allowing yourself, then this is the optimal tree. Well, not tightly, but like you need order of n squared to solve this problem. If this is the type of question you're allowing, so the question then becomes, what if we allow more elaborate questions? So what if our questions become just slightly more complex. Would that change anything? And the answer is yes. The answer is yes if we allow to comparing sums of just constant number of elements. We can get this thing to n to the 1.5, and there was a recent paper how to get it to almost linear, to n times some polylog. We will definitely not discuss that paper. It's really complicated, but we will try to understand a little bit about how to get that down to n to the 1.5. All right. So, how can one make the decision tree better? So, what we need is something. It's a wonderful and at the same time ridiculous piece of math that has its own name. It's called a Friedman Streak. Friedman Streak is just like weird thing to write down, but it's just this. If you want to compare four numbers, a plus b, if you want to ask if a plus b is at least c plus d, right? Instead, which closely, you can ask if a minus c is greater than d minus b. So those things are equivalent. And yes, that is a Friedman Streak. So how can you use something like that? It is fascinating, to be very honest. What we do, and again, I'm not trying to give you the entire description of the decision tree, just the main ingredients that if you use enough work will actually come together and create the algorithm, or in this case the decision tree. So one way to solve the three-sum problem is to look into those two arrays, right, B and C, and then create one huge array of all the elements of the form Bi plus C, Bj plus Ck. So I can put all the elements of that form into an array, right? And then I can sort it into, so create a sorted array with values of this form. The array has of size n square, so it will give me the complexity of like n square log n, something like that. All right, and then I can take all the elements. So I have my array A, so I can take my element A1 and do the binary search to look A1 in the array of B plus C. It takes me about log n time, so I can do that over and over again. So I do it for A2, then for A3. So then in time n log n, I will have an answer. So what I'm looking for is not the A1. So I'm asking is there element of the form bj plus ck that is equal to minus a1. Right, so we're asking this question, then we go to a2 and ask if minus a2 belongs to the array of this b plus c's, and then so on. So the algorithm of looking for a's, or like minus a's in the b plus c, takes very short time. It takes about n log n. So the problematic part is that we need to create and store and the worst part to sort the b plus c. That is the part that is taking the whole lot of time. So if we can find a way to sort that thing without spending that much time, that would be fantastic. So how can a decision tree sort b plus c without actually do the sorting? Well, to do this, you need to, so to sort b plus c's, you just need to have answers to the following questions. You need answers to the questions of this form. So suppose you knew all these answers, then you don't need to answer questions about, or to ask questions about them. So if you already know the answers to those questions, then you already know the sorting of this element. Again, the decision tree model is a non-uniform model. It doesn't care about the computations that are going into constructing the decision tree, or figuring out the next question, or how to get answers out of the questions you did so far. What we're just interested is the existence of this giant object that is decision tree, such that if you just answer questions, you will get to the right answer, right? So what I'm saying again is that if I can answer those questions, I can have the sorting of this. I don't need the sorting to do sorting by hand if I know the answers to this question. So how can I get this? And again, this is where the Friedman streaks come into play. All right, so we need to sort. So to answer this one, we need to answer the questions of the form bi1 minus bi2 less or equal to ck2 minus ck1. Right? Right. So what we actually need to do is to find out the answers to all the questions of those forms. So those two are equivalent, and that is the simplistic beauty of the Friedman streak. So we change the question that is about sums of elements from different groups to the question about comparing elements from the same nature, right? So that's what it is. Okay. So now what you need to do, you need to make this array that, so you need to create, so the whole idea of this decision tree is to be able to answer questions of this form. And then use that to answer questions of this form. And use that to have a sorting of this. And then use that to look up the elements of A using binary search in that sorting of B plus C's. All right, so now I just want to say where the n to the 3/2 come into play. The idea is that we cut our arrays, our A, B, and C, our B's and C's into these pieces of size square root n, right? And then what I need is, so we have B1, B2, and so on up to B square root n. And then we have C1, C2, C square root n. All right? So, what can we do about it? If I have this element A1 that I want to find in, as if there is some B and C that sum up to minus A1, well, first of all, I can easily find such J and K. Let's use some P and Q, right? Such that C P such that B P plus CQ can contain A, right? Find all P and Q such as BP plus CQ. That means, right, so that is just a way of saying that set of all the B plus C such that B belongs to BP and C belongs to CQ can contain minus A1. So moreover, I will say without proof that there are at most square root order of square root n. So at most order of square root n such pairs. All right. So the question is now that I need to look up an element minus A1 in this set. So as I said here, the whole point is that we want to have that ahead of time. I don't want to compute those sets and then sort them and that would be awfully long. So instead what I do, what I do is I have those sets so let B prime I be the set of, let's say, x minus y, where x and y both belong to Bi. Right, and then I have Ci prime to be the set of x minus y, where both x and y belong to Ci. So far so good, and now what I just need to do, then this is the most crucial step. As I said, D would be union over all I of all B I prime and Ci prime. So the size of the D, and this is again a crucial part, the size of the D is, so I have a square root n sets B, square root n sets C, and so on, square root n sets B prime and C prime. Each is a difference of two elements in Bi. Bi has size square root n. That means Bi prime has size about n. So size of D would be order of n to the 3/2. So now, basically, the main step of the decision tree is, so this is basically almost the only thing that our tree does is, because at least the only time-consuming thing, it sorts D. After we sorted D, we know relationship between all differences of elements, so as long as they belong to the same piece of the size square root n. That means that we can answer. So if I am asking, if I want to sort this set, I need to answer questions B, right, B1 plus C1 less or equal to B2 plus C2, where B1, B2 belong both to BP, and C1, C2 belong to CQ. So this, once again, Friedman Streak, we switch to B1 minus B2 less or equal to C2 minus C1. And this is a question that by definition of D, we know from the sorting of D. Because we know the sorting of D, we know the answer to this question. And because we know the answer to this question, we know the answer to this question. That means that we can answer any questions that can arise while we would want to sort this set, which means that we already know the increasing order on this set, which means that we can do the binary search on this set. So then the algorithm is to take element A1, find all the pairs BP such that it's possible for BP plus CQ, all the pairs PQ such that all the BP plus CQ can possibly contain A1, the rightmost square root n of them, check them all, use the binary search to find them, go to the next one. That's it. That's the whole algorithm. I know that might be a little heavy-handed, but that is a beautiful way that we can do something with decision trees that we couldn't do with algorithms. Okay, now to the most exciting part is that this is not for the amusement's sake only. We can actually use that there is a non-trivial decision tree to speed up the algorithm, and that is super exciting. So all right, so what is good decision tree for? Well, it can solve our problem really fast. What's it bad for is that it is enormous. So we have the decision tree. We have the decision tree of the depth order of n to the 3/2. Well, we also have log n here, so wavy O means that I don't care about log factors as well as the constants. So which means that the size of the decision tree is exponential in the depth. So it is enormous. It's just so huge. So why is that still interesting? That we will not use it for our original inputs. We will construct the decision tree explicitly for some size t, such that 2 to the t to the 3/2 log t would be equal to n. So I pick t such that this would happen. So t would be equal to the log n to some degree. We would, well, yeah, that I'm going to tell you more of like proof of concept rather than a very elaborate, fine-tuned thing. So what I'm just saying that there exists alpha more than 0, something like 2/3 that this would be true. How can I use that? So I can construct such a decision tree. We didn't discuss it while we were talking about decision tree because we kind of just say, hey, we don't care. But in fact, all the things I said couldn't be translated into construction of the decision tree. So now how can we use it? Well, we have our array, well, 3 arrays. We can split it into groups of size t. Right? So now I want to find all the triples of groups that could potentially contain my solution. And it turns out that there are not too many of them. So the number, I mean, you can assume because I have n over t groups, one can assume that that could be up to n cube over t cube triples that could potentially have my solution, which is not correct. In fact, if you do the analysis correctly, you will get order of n square over t square triples that could contain my solution. Right? Fantastic. And now, what I'm going to do, I'm going to say, hey, if I use the standard algorithm that runs in n square time, like the algorithm that is identical to the first decision tree that we made, that would be n square over t square times t square, which is the time that we need to solve the problem on the instances of size t. That will give me n square, which was kind of back where we started. But now I have this decision tree of depth t to the 3/2. So I can solve the whole thing in order of n square over t square times t to the 3/2, which brings me to n square over square root of t. So the larger t I can get, the more of speed up I can have. Basically, my bound on t is that I should be able to construct this decision tree in a given time, which actually brings me that t should be like some degree. So alpha is roughly 2/3. So this you would have something like that. Just log. In fact, that would be just log t. So that would give you something like n square. Well, again, my analysis is a little shady, but that would be something like n square over log n to the 1/3 times log n. That might seem to be super close to n square, but that was the very first improvement over n square for this algorithm, and it comes from this understanding of other computational models. And this is not the only example. We have a rather recent breakthrough for some graph problems, where by understanding the circuit complexity, how certain problems are computed by circuits, we can suddenly use some super clever ideas and speed up the computational graphs. And that just tells you that this, the broader the horizon you have, the more intriguing tools you can bring to the algorithmic design. And that was my overview of the basics for the algorithms and computational complexity. So we went through few ways to create algorithm. We have brute force, we have dynamic programming, we have local search. We have used some obscure computational model to speed up your algorithm. Yeah. And we went through a couple of different computational models as cover of, what is computational complexity rather than algorithms. So I hope you enjoyed it, and I hope that you find that useful. See ya.